Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 26, Journey to the Center of the Earth. Now that we've seen what's happening on the surface of the Earth, let's talk about what's going on deep down inside the Earth and how we know about what's going on deep down inside the Earth. Later, as we talk about the other terrestrial planets, we will talk about how they are similar to or possibly different from the Earth in their internal structure. So the first thing is I've already shown you this model of the Earth. We've got a solid inner core surrounded by a liquid outer core. Then surrounding that is the mantle of the Earth, and the upper mantle is a very ductile or plastic layer called the asthenosphere, where the rocks can actually flow and move. And sitting on top of them is a rigid part of the mantle called the lithosphere that carries with it the crust on top and creates our tectonic plates. So how do we know that this is the structure of the Earth? How do we know what's going on deep down inside the Earth? So I want you to answer this question learning catalytics. How do we know what the interior structure of the Earth is like? Is it A, we've drilled deep holes or have deep mines that penetrate nearly to the core? Is it B, sound waves travel through the Earth and probe the interior? Is it C, X-rays travel through the Earth and probe the interior? Is it D, mysterious particles called neutrinos penetrate through the Earth and probe the interior? Or is it E, the interior structure is based on theories but has not been observed? So go ahead and take a moment to answer this question in Learning Catalytics. All right, so what did you come up with when answering this question? The first one I can tell you is that the interior structure of the Earth has been directly observed. It is not E, the interior structure is based on theories but has not been observed. And in particular, in E, I use the word theories as we use it in our everyday life, a speculative idea that isn't well proven. In science, and in particular in my classes, I try and never use the word theories in that way. I always try and stick to the scientific definition of a theory, which is backed by a substantial amount of evidence. So it turns out, although we do model the interior of the Earth, we can compare that to direct observations of what's going on down at the center. Now, your first thought might be that we have mines that go deep enough or holes that have been drilled deep enough to tell us what the inside of the Earth is like. So let's examine those first before we come back to the right answer for this. So what about mines? What's the deepest mine on Earth? The deepest mine in the world is AngloGold's Ashanti's Mponeng gold mine, and it's southwest of Johannesburg, South Africa. It's about 4 kilometers deep, which is about 2.5 miles deep. Now, here's a picture of what the mine looks like, the surface of the mine up there at the top. The thing about this mine is, down at the bottom, the temperature of the rock face is about 151 degrees Fahrenheit. That is, they're deep enough underground that as you get underneath the ground, the temperature gets higher and higher and higher. So at this depth, 4 kilometers, the rock face is 151 degrees Fahrenheit. Now, humans can't survive at those temperatures, so they have to air condition. They have to bring air down to the shaft to cool it off, and that air conditioning cools the air to about 86 degrees Fahrenheit. And a trip from the surface down to the bottom of that mine takes about an hour. And there are a number of videos you can find online giving you tours of this mine to show you what it's like 4 kilometers beneath the surface. But now keep this in mind. The radius of the Earth from the center to the surface is 6,378 kilometers, which means in this mine, we have dug 4 kilometers deep. We have gone from the surface, which is 6,378 kilometers from the center, down to 6,374 kilometers from the surface. That is, this mine, only being 4 miles deep, has barely even scratched the surface of the Earth. The thing is, we haven't done much better with drilling. The deepest hole that humans have ever drilled on the Earth was a research drill, and that was called the Kola borehole. It's on the Kola Peninsula, which is near the Norwegian border, and the Russians dug the deepest well on Earth. Now, they picked this particular location because they wanted to drill down into the mantle for scientific purposes to bring up mantle rocks to learn more about the mantle of the Earth. And to do this, they had to drill many kilometers below the surface. And in this particular case, the well was 12,262 meters deep. That's a little over 12 kilometers or 7.5 miles deep, and it was drilled from 1970 to 1989. But again, the distance to the center of the Earth is 6,378 kilometers. This drill hole only went 12 kilometers below the surface. And so it barely, again, scratched the surface of the Earth. The hole is only 0.19% of the way to the center. So even with the deepest hole on Earth, we have not drilled even close to 1% of the way down to the center. Now, unfortunately, they had a lot of troubles with the Kola borehole, and eventually the project was shut down, and the buildings that you see here have since been destroyed. And today, all that is left of the Kola borehole is this little well cap right here. But the building that that it used to be housed in down here has now been destroyed, and that is the top, the cap, on the deepest hole that humans have ever drilled, going 12 kilometers down below the surface. So how is it that we know what's going on deep down inside the Earth? Well, it turns out we use sound waves, but we don't usually call them sound waves. In the case of probing deep down inside the Earth, we call them seismic waves, waves that are generated by earthquakes. So earthquakes generate different kinds of waves. They generate P waves and S waves and surface waves, and we'll talk about all of those in a minute. But here's a little bit. We'll talk about the waves in detail in a second. But let's talk about some of the general idea of what happens. First of all, imagine that an earthquake occurs somewhere on the Earth. In this particular example, it occurs in Mexico. When that earthquake happens, it sends sound waves, two different kinds of sound waves, P waves and S waves, through the Earth. And those waves take time to propagate through the Earth before they arrive at our location. Now, the P waves arrive first. They travel faster through the Earth. The S waves arrive second. They travel slower. And the length of time that it takes them to get to us and the strength when they arrive tells us something, not only about the earthquake, but what is going on deep down inside the Earth as those waves travel towards us. So we can learn what's going on deep underneath the Earth by following these waves. Now, as an example of an earthquake, let's talk about the famous August 23rd, 2011 earthquake right here in Central Virginia. For those that weren't here at the time, and I know most of you weren't, it was a magnitude 5.8 earthquake, and it was located in Louisa County, Virginia, which is the next county over from Albemarle County, where the University of Virginia is located. It wasn't very far from the university at all. Now, fortunately, here in Charlottesville, we suffered very little damage from this earthquake. And the same can't be true of Louisa, can't be said of Louisa County. They suffered tremendous damage in Louisa County, and a lot of damage was suffered even as far north as Washington, D.C. But a couple interesting things. Here are different seismograms from different seismological observatories located throughout Virginia. So let's take the one at Virginia Tech here for a moment. So you'll notice the earthquake happens over here at time equals 0. And at Virginia Tech, it took some time before the P waves arrived. In fact, you can see here that it took about 100 seconds for the P waves to arrive. The P waves arrive and the seismometer starts shaking. And it takes until about 130 seconds before the S waves arrived at Virginia Tech. And those were the second set of waves that arrived. And you'll notice that the closer that the station was to Louisa County, the faster it was that the waves arrived. So that's just a little bit about that earthquake. So that was a moderate magnitude 5.8 earthquake. It was at 1:51 p.m. on August 23rd, 2011. Interestingly, I was teaching Astronomy 1210, Introduction to the Sky and Solar System, in one of the lecture halls over in Minor Hall that day. Class began at 2 o'clock. It happened to be the very first class of the semester, so I had gotten there early to get set up and get the computer ready for class. And as I was setting up the computer, the whole building started shaking. Now, that summer, there'd been a lot of construction at UVA. In fact, I guess I should say every summer there's a lot of construction at UVA. But I thought initially that was construction going on nearby. But one of the students pointed out to me that they thought it had been an earthquake. So I brought up the U.S. Geological Survey website, and sure enough, an earthquake had occurred in Louisa County, about 30 miles east of Charlottesville. As I said, we didn't suffer much damage. The way that this earthquake happened was, you'll notice that the earthquake was here in Louisa County, about halfway between Charlottesville and Richmond, a little closer to Charlottesville than it was to Richmond. But most of the severe shaking, which is shown by the color on this map, was north and east of the epicenter of the earthquake, and it stretched all the way up to Washington, D.C. Some of you might remember the stories that the National Cathedral in Washington, D.C. suffered severe damage and was actually closed for a long period of time before it could be repaired, and the Washington Monument suffered damage as well from this. Now, fortunately, in Charlottesville, we were much closer to the epicenter than they were in Washington, D.C., but the exact way that this earthquake occurred, most of the shaking went north and east, and Charlottesville suffered very little damage. It was the strongest earthquake in our area. In fact, the strongest earthquake east of the Rockies since 1897. All right, so let's talk about these two different kinds of seismic waves. There are P waves, which are also known as primary or pressure waves, and then there are S waves, which are known as secondary or shear waves. A couple things about these. Let's talk about the different natures of these two waves, and then we'll come back to some of the other points in a second. P waves are pressure waves. It's what happens if you take a spring like this and you push the spring and pull it back and push it and pull it back. Really what you're doing is you're compressing it and rarefying it, compressing it and rarefying it. And as you compress the spring, that compression will actually travel down the length of the spring. So here's the compression, and then a second later the compression is there, and a second later, as you push on it, that compression will fall down, will travel down the spring. Shear waves, or S waves, are side-to-side motion, secondary waves. That's when you take the spring and instead of pushing and pulling on it, you shake it side to side. And that's what you typically think of as like an ocean wave, a wave that's going up and down like that. So here's a video that's going to show us the difference between P waves and S waves. So let me bring this over here and expand it. So this first example, these are P waves, where you compress the spring and you can see the compression traveling down the length of the spring and reflecting on the other end. And this is an S wave, a shear wave, where you're moving it side to side, and now you can see that displacement as it travels down the spring. So those were the difference between P waves and S waves. Okay, so P waves penetrate both solid and liquid rock. They can go both through solids and through liquids, and they're bent by changes in the structure of the earth. S waves, on the other hand, don't penetrate through liquids. You can think of the liquid core of the earth. If you think about it, it's very dense rock. It's liquid. It's very, very viscous. And if you think about molasses or some kind of very thick syrup, you can imagine that S waves like that will damp out very quickly in a very, very thick, very viscous liquid. The other kind are surface waves, and they travel only on the surface of the earth, and they don't penetrate deep down inside the earth. So surface waves don't tell us anything about the interior structure of the earth. That said, they're very important for earthquakes in that they cause a lot of the damage of an earthquake. But in terms of determining the structure of the earth, surface waves don't tell us about the interior. All right, let's take a look at a video about how these waves tell us about earthquakes. Or tell us about the interior structure of the earth. So let's watch a video that tells us how these seismic waves tell us a bit about the interior structure of the earth.
Body waves from distant earthquakes travel a curving path through the earth, arriving at seismic stations from below. The compressive motion of a P wave is in the direction the wave travels, thus the motion of the seismometer will be mostly vertical with little horizontal motion. The S wave has a shearing motion perpendicular to the ray path, thus the S wave produces chiefly horizontal movement. Surface waves travel in an undulating pattern across the surface of the earth, producing up, down, back, forth, side-to-side motion. The seismogram merely depicts motion, not direction of motion. The movement of the building is exaggerated to show the relative motion of each wave, only detectable by seismometers at this distance.
The important thing to note about this video is that the P waves and the S waves travel through the Earth to get to the seismometer. So if an earthquake occurs in a distant part of the world, those P waves and S waves travel through the Earth. And because they travel through the Earth, that allows us to probe the structure deep underground. By the way, you might be interested in learning why the waves curve like this. And the reason the waves curve like that is that as we get deeper and deeper below the surface of the Earth, the rocks get denser and denser. And as the material gets denser, that causes the waves to bend. And that's why these waves bend and then return back up to the surface. All right, so let's go back to our lecture notes here for a minute.
Body waves from distant earthquakes travel a curve.
Okay. So, as these waves travel through the Earth, they allow us to probe what's going on deep down underneath the surface. Now, as an example of P and S waves, let's talk about my voice. My voice is carried by sound waves. What are sound waves? Are sound waves pressure waves? Are they shear up and down secondary waves? Are they a combination of both? Or is it neither? Sound is an electromagnetic wave. Take a few seconds to answer this question. All right, what did you come up with the answer for this one? Well, it turns out that sound waves are in fact pressure waves, and that is how we generate sound. Let me give you an example of this. Here's an animation of how a speaker works. The way a speaker works is you take a large diaphragm or cone right here, and you move the cone back and forth. And you move it back and forth using a magnet with a coil that has wire wound around it. And when you run electricity through a coiled wire, it generates a magnetic field. And that magnetic field can either be attracted to or repelled from the permanent magnet inside the speaker. So here's the permanent magnet right here, this large black cylinder is the permanent magnet. Here's the coil of wire, and it's connected to our source of sound, our stereo, for example. And as electricity runs through this, it either generates a magnetic field that is attracted to the magnet or repelled from the magnet, and it pushes that cone in and out. By pushing that cone in and out, when it pushes the cone, it compresses the air, and when it pulls the cone backward, it rarefies the air. That's what my vocal cords are doing. My vocal cords are squeezing and releasing the air. They're compressing it and rarefying it and compressing and rarefying it. And that's what sound waves are. So sound waves are an example of pressure waves or P waves. Now, as I said, both the P waves and the S waves, they travel through the Earth and they appear on the surface at some distant station where they're measured. And the length of time that it takes them to travel through the Earth and how they bend and even get reflected inside the Earth tells us all about the deep interior structure of the Earth. So, for example, imagine that there's a giant earthquake somewhere on Earth. As the P and the S waves travel through the Earth, we mentioned that only the P waves and not the S waves make it through the liquid core. So for a large significant fraction of the Earth, opposite the earthquake, there are no S waves detected, and there are no S waves detected because they don't travel through that liquid core. And in fact, that is not only how we know that there's a liquid core, but that is how we know the size of the liquid core. We know how big the liquid core is by carefully measuring earthquakes at many different stations, using the physics of how the sound waves travel through the Earth and using that to determine how big the liquid core is. We can do the same thing for the inner core. As the sound waves travel through this inner core, they can reflect off of and will bend differently through the inner core. That allows us to measure how big that is. And we can also from this find out much more detail about all the different layers underneath the surface of the Earth. Now, we're not going to concern ourselves with all the different layers and discontinuities that we find deep inside the Earth. Mostly what I just want to point out is that from earthquakes, we have learned that the inner core is about 2,500 kilometers across. That's about 20% the diameter of the Earth. The liquid core is about 7,000 kilometers across, and it's about 55% the diameter of the Earth. And then the mantle out there forms most of the rest of the Earth, because you'll remember that the crust is very, very thin, typically maybe 10 kilometers over the oceans and maybe a few tens of kilometers over the continents, but very, very tiny compared to the diameter of the Earth. This is why we would also like to put seismometers on other planets. During the Apollo missions, seismometers were placed on the surface of the moon, and they operated for a number of years. And as spacecraft were intentionally crashed into the moon, and as occasionally bodies collided with the moon, they generated moonquakes that allowed us to study the interior of the moon. But up until recently, those were the only two planets, the Earth and the Moon, where we were able to measure what was going on inside the planet thanks to seismic waves. But recently, within the past few years, we have landed a probe on Mars called Mars InSight. And the whole goal for the Mars InSight mission is to tell us what's going on deep down inside of Mars. Now, InSight is actually an acronym, and it stands for the Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport. So the Mars InSight mission is a lander. It's not a rover. It's a lander on the surface. It's not going to rove around. And it's going to deploy two main scientific instruments on the surface. The first of those instruments is a seismometer, the most sensitive seismometer ever sent into space. The other instrument that is going to be placed on the surface is a heat flow probe that tells us how much heat is coming out of the interior of Mars. So we'll talk about both of those in a second, but let's talk a little bit about InSight's history. Interestingly, it was supposed to be launched to Mars in 2016, but they missed that launch window because it turns out the seismometer wasn't ready. The seismometer had significant problems with it. In particular, it wasn't able to maintain its vacuum, and they were afraid that if they launched it to Mars in the way that it would lose its vacuum and would no longer be sensitive. So the French Space Agency, CNES, the seismometer instrument, kept losing vacuum, so they had to delay the mission. And because opportunities to launch to Mars only come around every 26 months, they missed their 2016 launch window and had to wait until May of 2018. And that cost $150 million for the delay, bringing the total cost of the mission up to $830 million. The spacecraft was launched in May of 2018, and it arrived at Mars in November of 2018 and successfully landed on the surface. And the goal of putting a seismometer on the surface of Mars is to use Mars quakes to measure what is going on deep down inside of Mars. Now, what we dearly love is what we have on the surface of the Earth, a series of seismometers all over the surface. But the problem is launching spacecraft to Mars is complicated enough and expensive enough that we don't yet have a network of seismometers on the surface of Mars. Maybe that's something that your generation will do, is build the first network of seismometers on Mars. But for now, we're lucky to have one on the surface. So InSight was launched back in May of 2018. It arrived on Mars in November of 2018. It was placed on an elliptical orbit that took it out to the orbit of Mars, and then caught up to Mars there, or Mars caught up to it, I should say, and InSight landed on the surface of Mars. This is a picture of what InSight looked like before launch, so we can see the spacecraft itself mounted inside the aeroshell. Here are the landing legs that you can see underneath it. Down below it will be the heat shield attached to the bottom, and this is the heat shield. It's not on there yet, that allowed it to enter through the atmosphere on Mars and safely make it down to the surface. And that's basically what the entry, descent, and landing looked like. Sitting on the surface of Mars, it is powered by solar arrays. So there are two solar arrays that are powering Mars InSight. And here are the two scientific instruments, the seismometer on the surface and the heat flow probe. The seismometer, we've already seen what they do. They measure shaking from earthquakes or Mars quakes. The heat flow probe is something really interesting. It's essentially a very fancy thermometer, and it measures the amount of heat coming out of the interior of Mars. And it turns out it's a very, very simple number, but it tells us a tremendous amount about the interior of the planet. The problem is up here on the surface, you can't measure easily how much heat is coming out of the interior because you're dominated by warming and cooling, warming from sunlight and cooling from the ground radiating its temperature out at night. But if you can bury the heat flow probe just a few meters underground, you are insulated from what's going on with the day-night cycle on the surface, and then that tells you very accurately how much heat is flowing out of the interior of the planet. And that can tell you a lot about whether the interior is molten or not. Now, because this was a seismometer and a heat flow probe, they didn't have to go anywhere special on Mars. They didn't have to pick any particularly interesting region, and so they landed on Elysium Planitia. Elysium Planitia is basically just a big flat area on Mars. They wanted to find a nice, flat, safe area to land the probe so that there wasn't any danger that it would tip over on landing. Here are the spacecraft that we have landed on the surface of Mars. So here is the Curiosity rover that is currently driving on the surface. And InSight is actually not that far north of Curiosity. Of course, Curiosity is never going to get there. It has its own mission. It's exploring its region, which is quite interesting. It's not going to drive way out hundreds of kilometers out onto the plains out here to get to InSight, but that's where the two of them are located. And then here are some actual images that were returned from InSight from the surface of Mars. So here we see one of the solar arrays after deployment. Here we see the seismometer package being placed on the ground. And then on top of the seismometer itself, there is a shield that goes over it, and this shield is both a thermal shield. It prevents the sunlight from heating up the seismometer and prevents the seismometer from cooling off too much at night. It also shields the seismometer from the wind blowing on Mars. This is the data cable that is bringing back the data from the seismometer. And then this is the heat flow probe being placed down on the surface of Mars. The heat flow probe has a mole on the end, and the mole is a little cylinder, and it has inside essentially a jackhammer. And the goal for that jackhammer is to hammer itself into the ground. Now, unfortunately, since the probe arrived in 2018 and they tried to deploy the the heat flow probe in 2019, we've been having a lot of trouble with the heat flow probe. The soil on Mars does not behave like soil on Earth. And the way the probe was supposed to work is that little hammer was supposed to fire itself, and that would push the probe deeper every time. And then friction with the surface would prevent the heat flow probe from backing out. And the problem is the soil on Mars is compacting so much that it is not encountering any friction, and the heat flow probe is not burying itself underneath the ground. NASA has tried a number of different things to try and bury the heat flow probe. The latest one is actually using the robot arm to push on the top of the probe to try and push it underground and get it buried deep enough that it could start burying itself. We'll see here in the next few months whether they have any success with that. So the seismometer has detected some Mars quakes, some quakes on Mars already, but they're still trying to work on deploying the heat flow probe more than a year after landing. All right. So we've already talked about the fact that this is the structure of the Earth. One thing I want to talk about is, where does the heat at the center of the Earth come from? Why is the center of the Earth so hot? In fact, the center of the Earth, this inner core down at the very center, is about 6,000 degrees Kelvin. 6,000 degrees is the same temperature as the surface of the sun. Why is it that the inner core of the Earth is so hot? Well, there are three sources. Those three sources are accretion, differentiation, and radioactivity. Accretion is how the Earth formed. It's when bodies, comets, and asteroids struck the Earth early on. And as a body like that strikes the Earth, its kinetic energy, its energy of motion, is converted into thermal energy. Obviously, the surface gets really hot. And you can imagine over billions of years, after being bombarded billions and billions of times by giant comets and asteroids, that will have a tendency to heat up the surface. So that is the heat of accretion. The heat of differentiation is where the heavier materials sink to the lower parts of the Earth and the lighter materials float to the surface. And that primarily comes from converting the potential energy of all those heavy elements into, as you convert that potential energy, as they fall down to the center, they convert that energy into thermal energy. So as the heavy elements sank to the middle and the light elements, the light materials floated to the surface, that released heat as well. And then the last one, and of both of these, it turns out that accretion and differentiation are no longer important for heating the Earth today. Most of the accretion and most of the differentiation happened in the early history of the universe. Now, they are responsible for heating up the Earth early on, but they're not generating substantial amounts of heat today. Today, the vast majority of heat at the center of the Earth is generated by radioactive decay. There are radioactive elements deep inside the Earth, and as those elements decay, they release heat. And because they are buried deep inside the Earth, it is difficult for that heat to escape. So, largely the core of the Earth today is leftover heat from accretion and differentiation, and heat that's being generated by radioactivity today. You might wonder, how does the Earth lose heat over time? Well, there are three processes for losing heat. One, and the most important one, is convection. Convection is where hot material rises up and then cools off and sinks back down. And in a planet like the Earth, convection is a significant source of transporting heat from deep down in the core up to the surface. Another one is conduction. Conduction is where heat simply travels through the material. It's not the bulk motion of material. It's that it's a really good example of conduction is if you take a piece of metal and you heat up one end of the metal and you're holding the other end of the metal, heat will conduct through the metal. And conduction is another way that the Earth loses heat. That one is much less efficient than convection. Convection is a much more efficient way of transporting heat from the core to the surface. Finally, once that heat is up on the surface, it is lost through radiation. Radiation is where the surface of the Earth is warm enough that it gives off infrared light. And as that infrared light escapes into space, it cools the surface of the Earth off. Now, there's another way to study the interior of the Earth, and the other way to study the interior of the Earth is by using the Earth's magnetic field, because the Earth's magnetic field is generated deep down inside the Earth. So let's talk about the Earth's magnetic field first, and then talk a little bit about how it's generated. So what do we mean by a dipole magnetic field? If you take a battery and take a wire and wind that wire around a piece of iron or a piece of metal, you can generate a magnet. As you run electricity through that wire, that is, as you hook up that wire to the battery, as electricity runs through this coil, it will generate a magnetic field. And that magnetic field will have a north pole and it will have a south pole. And that's what we mean by a dipole field, a field that has one north and one south pole on it. So if you run electricity through a coil like this, in science or in engineering, we call a coil like this a solenoid. If you run electricity through a solenoid, it will generate a magnetic field. Okay, so how do we generate that field inside the Earth? Well, it's generated by electric currents that are generated in the core of the Earth. And those electric currents come from the fact that the Earth has a liquid iron core. And iron is an excellent conductor of electricity, and it is molten, so it is flowing and moving around. And as that liquid iron core moves around through convection, and as the Earth spins very rapidly, the combination of convection and spin with a molten material that is a very good conductor generates our magnetic field. So it's the combination of convection and rotation that's enough to move the electrons in the iron atoms. Those electrons, of course, are the negatively charged electrons in the atoms, and they move in the same way that they do in an electromagnet, and that generates the Earth's magnetic field. And it is generated in the liquid core. So here you'll see the mantle of the Earth. This is not the Earth as a whole. This is just the liquid core of the Earth. There's the mantle. The magnetic field is generated in that liquid core. So by studying the Earth's magnetic field, we can actually study the liquid core of the Earth. Now, since the Earth rotates rapidly and has a large molten core, it has the strongest magnetic field of any of the terrestrial planets. And here's a picture again of what's going on deep down inside the Earth. So we have these convective currents. We have the hot iron rising up, cooling off and sinking back down. Again, the hot air iron rising up, sinking off and cooling down. Because it's molten and it's liquid, it can move around. And the Earth is spinning very, very rapidly. So that rapid spin, along with that convection, generates these currents, and that generates the Earth's magnetic field. So I want you to answer this question for a second. Which of the following most likely explains why Venus does not have a strong magnetic field? So Venus is about the same size as the Earth. We would expect that it would have a molten core, just like the Earth has a molten core, because it's about the same size as the Earth. But why does Venus have or a very weak magnetic field compared to the Earth? Is it A, too close to the sun? B, is it too small? C, is its atmosphere too thick? D, it does not have a metallic core? Or E, is its rotation too slow? So take a minute to answer this question in Learning Catalytics. All right, welcome back. So what did you think about this one? Well, it turns out that the answer to this one is probably E. Its rotation is too slow. As we will see in the lecture on Venus, Venus rotates incredibly slowly compared to the Earth. The Earth rotates on its axis once every 24 hours. Venus, on the other hand, takes over 200 days to rotate on its axis, much, much slower than the Earth rotates on its axis. So Venus very likely has an interior molten core, just like the Earth does, because Venus is about the same size as the Earth. It has about the same composition as the Earth has, so we would expect the interiors to be similar. It's different, however, in that its rotation is much, much slower. For most of the bodies in the solar system, the answer to this question, why they don't have a strong magnetic field, is because they either don't have a metallic core or they're too small. Our moon is an example of a body that is so small that it has cooled off over time. The rate at which a body cools off depends on the ratio of the surface area to the volume of the body. The more surface area you have, the faster you cool off. But the more volume you have, the more capacity you have to store heat. And it turns out for smaller bodies, their volumes are small enough that they don't have the capacity to store a lot of heat. And relative to their volumes, their surface areas are big and they can radiate all that heat off into space. Bigger bodies like the Earth have a smaller surface area compared to their volumes, and it takes them longer to cool off. All right. Not only does the Earth have a magnetic field, but it turns out our magnetic field is changing. Both the orientation and the strength of the Earth's magnetic field vary over time. The north and south magnetic poles don't align with the geographic poles on the Earth. And we saw this earlier in the semester. The North Magnetic Pole is currently drifting about 20 kilometers every year. And we saw a graph like this earlier in the semester when we saw that over the last few hundred years, the magnetic pole on the surface of the Earth has been drifting. But really, for the last sort of 60 years or so, the magnetic pole near the North Geographic Pole has been moving very, very rapidly. And really since the 1990s, so for the last 30 years or so, it has been moving very, very rapidly. We don't know exactly why this is. It has something to do with how that magnetic field is generated deep down inside the core. Now, you've probably heard that every now and then the magnetic poles on the Earth reverse one another. And what we mean in those cases is that the North Magnetic Pole and the South Magnetic Pole switch places. So the magnetic pole that is the North Magnetic Pole becomes the South Magnetic Pole, and the South Magnetic Pole becomes the North Magnetic Pole. Over the last 330 million years, the poles seem to have reversed themselves about 400 times. And this is actually really interesting. The way we measure this is actually by using seafloor spreading at the bottom of the ocean. As the seafloor spreads apart, when those rocks are molten, when they're still molten, the Earth, they're impacted by the Earth's magnetic field. And when they solidify, they have locked into them the orientation of the Earth's magnetic field, not as it is today, but as it was when those rocks are formed. And what we see when we look at the mid-Atlantic ridge is that we see rocks that have, as the rocks were spreading out, we see rocks with the magnetic field oriented this way, right next to rocks with the field oriented this way, and then this way, and then this way, and then this way. And it turns out we can see the changing orientation of the Earth's magnetic poles in these rocks. So about 400 times in the last 330 million years, the poles have reversed. The time interval between reversals can be as little as 100,000 years and as long as tens of millions of years. So there doesn't seem to be, at least as much as we can determine right now, the exact mechanism as to why the poles reverse. In recent times, the poles seem to have been reversing about every 200,000 years. But the last pole reversal was 780,000 years ago. Now, some people have proposed that the rapid movement of the magnetic pole across the geographic pole of the Earth indicates that another polar shift, a magnetic polar shift, is underway right now. The truth of the matter is we don't know. It is interesting that the pole is moving very rapidly, and we haven't seen it do that since the late 1500s. But on the other hand, since pole reversals happen every 200,000 years, and we've really only been tracking the magnetic pole of the Earth for about 400 years, we really can't say how often the pole moves fast like this or moves around. Based on the geologic evidence, it seems that the field doesn't rapidly change. It's not as if you will wake up one Tuesday morning and you will see on the news that the poles reversed overnight. It's likely that the field changes very slowly over a period of roughly 5,000 years. And it seems like what happens is the poles wander across the surface of the Earth, and they wander to opposite sides of the Earth, opposite to where they were before. And this would be good because a very rapid change in the Earth's magnetic field, literally flipping overnight, would destroy much of our technology. It would destroy our power systems, our power grids, could damage satellites. It would set up huge currents on the surface of the Earth and in our power lines that could do significant damage. But a pole reversal that slowly happens over the course of 5,000 years probably won't be noticeable. I mean, we'll notice the magnetic field changing, but it wouldn't destroy our technology. Now, one consequence of the Earth's magnetic field are the aurora borealis, or the aurora. The sun is routinely emitting a wind, a low-density wind of charged particles. These particles consist of electrons and protons, which come from hydrogen atoms. They also sometimes consist of heavier elements like ionized helium or even some heavier elements, but mostly it consists of protons and electrons that are thrown off the surface of the sun. Now, every now and then, active regions on the sun can flare and fling large amounts of particles towards the Earth. And we'll see what happens there in a second. But our sun goes through a period of activity. Our sun goes through solar minimum and solar maximum. During times of solar minimum, there are hardly any sunspots on the sun. So here, for example, is an image of the sun in November of 2018. When we were at solar minimum, we are still at solar minimum today with hardly any sunspots. Sunspots are little black spots that appear on the surface of the sun. And sunspots are magnetic storms on the sun. And once every 11 years, as the sun goes through its cycle, we reach a period when there will be lots of sunspots on the surface of the sun. Now, those sunspots, those magnetic storms, can sometimes result in flares. So let's take a look at some images from the Solar Dynamics Observatory. The Solar Dynamics Observatory is the most capable solar observatory that we have in orbit today. Much of this video shows you images taken by the Solar Dynamics Observatory in the far ultraviolet portion of the spectrum. So before we see some of this far ultraviolet, let's take a look at sunspots on the surface of the sun. So this is a visible light image of the sun, and these dark spots that you see are sunspots. And those sunspots, in many cases, are larger than our whole planet. And what happens in a sunspot is it is a place where strong tangled magnetic fields on the surface of the sun poke through the surface. And those strong magnetic fields prevent fresh hot gas from getting inside the sunspot. So the sunspot can radiate its heat off into space, and hot, fresh gas cannot get in there to warm it up again. Now, although sunspots are dark, the sunspots are dark because they're cooler than the rest of the surface of the sun. And although these sunspots are cooler than the rest of the surface of the sun, by no means would we consider them cold. The surface of the sun is about 6,000 degrees Kelvin. Sunspots are still 3,000 to 4,000 degrees Kelvin, so they're still quite hot. They just look darker than the rest of the surface of the sun because they're much cooler. Now, sunspots often have associated with them solar activity, and every now and then the sun will flare. Here's an example of a solar flare, where these tangled magnetic fields suddenly snap and they fling particles at the Earth. And those particles, as they come towards the Earth, will interact with the Earth's magnetic field and the Earth's atmosphere to generate the aurora borealis.
Giant fusion engine that drives the solar system.
Okay. So, my next question for you is, have you ever seen an aurora? There's no right or wrong answer to this one. I'm just curious to find out how many students in the class have actually seen the aurora. So go to Learning Catalytics and spend a second to answer this one. Yes, I've seen an aurora, or no, I have not. Okay, so what generates the aurora? When the charged particles from the sun encounter the Earth's magnetic field, it turns out they're trapped by the magnetic field. They're caught in the Earth's magnetic field. A charged particle, a particle that has either a positive or negative charge, cannot cut straight across the magnetic field. In fact, when a charged particle encounters a magnetic field, it spirals along. It moves in a big spiral around the magnetic field. And since the magnetic field of the Earth comes down to the surface at the North Pole and comes down to the surface at the South Pole, those particles trapped in the Earth's magnetic field spiral around the field lines and they hit the Earth's atmosphere at the North and South Poles. And that's what causes our aurora borealis. So when the charged particles collide with molecules in the Earth's atmosphere, so as they spiral around these field lines, they spiral down and they come down to the surface, but as they hit molecules in the Earth's atmosphere, they excite those molecules to glow. And that glow is called the aurora borealis in the north or the aurora australis in the south. When the sun is particularly active, when we have major flares on the surface of the sun, it's possible to see the aurora borealis even here in Virginia. I have seen it 3 times from central Virginia in about the 25 years or so that I have lived in, 27 years that I've lived in central Virginia. I've seen the aurora borealis just 3 times here. Typically, you have to go much further north on the Earth. There is a ring of aurora around the north called the aurora borealis. Typically, it's visible from northern Alaska, northern Canada, Iceland, for example, and then Scandinavia and the northern Siberia. And then there is an aurora australis that is visible around the South Pole. That's much harder to see because there's not much land that is very far south except for Antarctica, and that is difficult to get to. But the aurora borealis can be quite beautiful. It can glow green and red. The green glow typically comes from these charged particles interacting with oxygen molecules in the atmosphere. The red glow can come from interaction with oxygen molecules as well. And then I have here some interesting aurora images that have been taken by various photographers over the years, just showing both the spectacular shapes and the spectacular colors of the aurora borealis. And then I think one of the most amazing things is actually seeing the aurora from above. This is a video that was taken by astronauts on the International Space Station showing you the aurora as seen from above.
The small step for man, one giant leap for mankind.
I think a couple of the more amazing things in that video, this particular sequence right here, I love because as you fly down, you can actually watch flying over a sort of the central United States and can see all the way to the eastern seaboard. So they're flying over Canada now. You'll notice here in the center, that is Lake Michigan with the city lights from Chicago. That's Milwaukee up there. And then as we look off into the distance here, we will see the lights of the eastern seaboard of the United States. So that's New York, Philadelphia, Baltimore, and Washington, D.C. These are lightning storms. You can see actually flashes of lightning in a giant thunderstorm. But in any case, in this you saw the aurora borealis as well. Let me finish by saying that the Earth is not the only planet that has aurora. In fact, many of the planets that have strong magnetic fields have aurora. Jupiter has the strongest magnetic field of any planet in the solar system, and it has tremendous aurora. We can actually photograph the aurora on Jupiter using the Hubble Space Telescope. Using an ultraviolet camera on the Hubble Space Telescope, we can actually see the aurora on Jupiter. In the case of Jupiter, there is both a northern aurora and a southern aurora. And some of these aurora, especially these bright spots that you can see in the aurora, are caused by particles that are coming off the moons of Jupiter. One of Jupiter's moons, Io, which you can see right here, Io releases charged particles, and as those particles are trapped by Jupiter's magnetic field and they come and strike the atmosphere on Jupiter, we see little bright spots underneath where that magnetic field connects Io to the surface of Jupiter. So that is a little bit about the interior of the Earth and how we determine what is inside the Earth. As we take our tour of the solar system, we will learn more about how the interiors of the terrestrial planets compare to the Earth. Next, though, I want to talk about the Earth's atmosphere and how the Earth's atmosphere compares to the atmospheres of the other terrestrial planets. So I will see you in the next lecture when we talk about atmospheres.